So in this example, we're going to be asked to do some dimensional consistency checks on a given equation. This is the kind of thing that's really common, for example, if we're looking at data sheets. There have been some examples in homework, for example, on this. So really common in manufactured data sheets, also for dealing with a formula that comes from some time ago, right? So this is from 1890. And one of the key pieces of this question that we're going to see here is this constant of 1.49. Which is specified in this problem, and it's going to play a key role in parts A and B here. So in part A, we're asked, is Manning's formula dimensionally consistent? We're going to see that we actually don't quite have enough information to say if this formula is dimensionally consistent. And so this is really asking us, under what conditions is this equation dimensionally consistent? And then in B, we're going to rewrite this into SI. But let's start with part A. So we have V is equal to 1.49 over N R to the 2/3 S to the 1/2. And now we're going to do our dimensional analysis here. Right, so this is going to be L over T, right, is our velocity, is equal to 1.49. So that's something where we don't know what the dimensions are yet. So we'll say the dimensions of that 1.49, which are unknown, over n. And now that's Manning's roughness factor. And in this case, this problem is referring us to chapter 10. If we go to chapter 10, we see that Manning's roughness factor typically has no dimensions attached to it. So that n, we're going to say, is dimensionless. R to the 2/3. So R is the hydraulic radius of the channel. That, as the name hydraulic radius implies, is dimensions of length. And then S to the 1/2. Now S is channel slope, so tangent of angle that the bottom of the channel makes with the horizontal. And that is typically given as a non-dimensional parameter as well. So it's also going to have this dimensions of 1. And I forgot on the L, that's actually going to have to be raised to the 2/3 power. Okay, so that's our expression in dimensional form. So we have the unknown dimensions for this factor 1.49 and everything else that we know plugged in, with a couple of non-dimensional parameters in this expression as well. All right, so let's figure out what the dimensions of 1.49 are in order for this expression to be dimensionally consistent. So we can rewrite this. So we're going to say the dimensions of this constant 1.49 have to be L over T. It's L over T times L to the minus 2/3. And if we simplify that, so we would say that the dimensions of 1.49 are equal to L to the 1/3 over T. So if if this constant has dimensions of L to the 1/3 over T, then this equation is dimensionally consistent. Otherwise, it's not. So again, that question is a little bit misleading, and we're really being asked there to find under what conditions is this expression dimensionally consistent. So let's move on to part B. So now in part B, we want to say, we're going to say that this 1.49 is valid if we're in BG, or British gravitational units, with n taken as dimensions. So we were told that n is typically dimensions. And now we're asked to rewrite this in SI form. So we know that 1.49 has dimensions of L to the 1/3 over T. In British gravitational units, this would be feet to the 1/3 per second. And we're trying to put this into meters per second. And so we have this expression 1.4 feet to the 1/3 per second. And now we're going to multiply by our conversion factor, right, times 0.3048 meters per feet per foot. That whole thing raised to the 1/3 power. And we're going to end up with then 1.00 meters to the 1/3 per foot. So that's the value that we get of the constant. A couple things to note here. This tells us that this expression was probably first derived in SI units. So initially, when this expression was derived in 1890, Robert Manning was probably working in meters cubed per second, not per foot. Got a little ahead of myself there. So this tells us that Robert Manning was probably working in SI units, or at least in meters and seconds, not at feet, because that would then make this the natural choice. The other thing to note here is that these are weird units, right? We don't often, outside of this kind of case or a data sheet or something, we don't often talk about, a length raised to the 1/3 power. That's one of the things that you really have to be careful about when you encounter something like this in real life.